All right, in this video, I'll be going through an AICE Physics Paper 2 question related to waves. And the question reads, state the difference between progressive waves and stationary waves in terms of the transfer of energy along the wave. So when we learn about progressive waves, we say, well, there's longitudinal and there is transverse. And that's like how the particles are moving related to the direction of transfer of energy. So progressive waves transfer energy, but stationary waves don't. They don't transfer energy. So that's the difference. Progressive waves transfer energy, stationary waves do not. Progressive waves do this. They transfer energy. Stationary waves not. Maybe a comma there. Not an English teacher, but I think that's a good right. So like maybe a coordinated conjunction here, and right? Any coordinated conjunction? Yet might be an appropriate coordinated conjunction. Progressive waves transfer energy, yet stationary waves do not. Or do you like progressive waves transfer energy and stationary waves do not? Yet or and? What did you say before? But? Okay. But stationary waves do not. Anybody would just forget a coordinated conjunction, two complete sentences. Progressive waves transfer energy, period. Stationary waves do not, and then it's understood transfer energy. However you want to word it, okay? Your own words, that's the key. But this is the idea. A progressive wave travels from left to right along a stretched string. Figure 4.1 shows part of the string at one instant. Q and R are three different points on the string. The distance between P and R is 0.48 meters. The wave has a period of 0.020 seconds. Determine the wavelength of the wave. So now they're showing it's not like the physical distance like from here up to here, but like this linear distance 0.48 meters. And so remember this key idea of like visualizing the waveform, how much of a wave do we have here, and then just setting that equal to the length. That's how we get wavelength, right? So it's like, okay, we'll start at P and we'll go up and back down. We're repeating right here. So there's one wavelength, like that's what we're after, this length right here. But I don't know how long that is. I just know that one, and then to get from here up to there, how much of a wave is that? Does anybody remember sort of visualizing this much of a waveform? From trough up to crest. That's half a wave, good. And you think about it like from crest down to trough or from trough up to crest. So that's half a wave right there. So I've got is one whole wavelength and another half of a wave. I've got 1.5 wavelengths, which is equal to 0.48. Perfectly solvable, right? So I'll rewrite it as 1.5 lambda equals 0.48 meters divided by 1.5, 1.5. And I can solve the wavelength lambda. Calculator check. 0.48 divided by little calculator check. Check the link in the video. I get 0.32 meters. All right, let's leave that working up there for a bit as we scroll down and see what we have to do next. Calculate the speed of the wave. Let's clear all that off. Let's remind ourselves, just calculated up here that 23. Like one calculation, especially in picture 2 where it's like this is part B, part B1, part B2. the velocity equals wavelength times frequency is the way we remember it. But let's remember what frequency is. Because frequency is 1 over the time period, it's really like velocity is the same way we've always learned it. Distance, wavelength, divided by time, right? Distance divided by time is velocity. So because frequency is 1 over t, like, oh yeah, that's why this is the same thing as that, right? Frequency is just 1 over t. So like this, sort of becomes that by playing this on. Remember how they gave us the time period up here, like 0, 2? So one way to think about it is just, calculating the, like this. 1 divided by 0.02, 50. Here's the wave frequency of 50 Hertz. 1.3 meters. Hertz is the same thing as reciprocal seconds. Meters per second. So when you multiply wavelength and frequency, you get the same units as velocity. Remember the idea of relating the base units. Derived units in the SI system. So those base units are the ones we want. And so 50 times 0.32 gives us a wave velocity of, don't write 4 squared. Just write 6. Don't make them do an extra calculation to check their answer. I wanted to record my answer as the square root of 256. No, don't do that. Don't make more work for the examiner now. Any questions on that? Leave it down in the comments below. Determine the phase difference between points Q and R. All right, so we have a progressive wave, right? There's direction of wave travel. There's a progressive wave, and so it's not just like, oh, adjacent loops are in or out of phase, right, with stationary waves. Here we have to sort of think about the phase difference between Q and R. Can anybody just look at this wave and go, oh, it's this? So here's Q and here's R. Wouldn't it be nice if R was right here? Like, what's the phase difference between those points? Let's just sort of think about that, and then maybe that's a helpful way to sort of get to the answer. What's the phase difference between this point Q and this point right here? Let's call it Q prime. Exactly, 0. Everybody didn't say anything because we know that the answer is 0. So it's like, no, nothing. I will just be silent. Well done, everybody. You don't even need to take a quiz tomorrow. Just ace it. All right, so this is, Q prime here is in phase, right? It's where the wave repeats. And so like there's 0 phase difference between these points. So we're really just considering, because these are 0 degrees different, we can say, well, what's the phase difference between like this point and this point? So how much of a wave is that? 1/4 of a wave. So a quarter is the phase difference, but they usually want it in degrees or radians. Okay, let's see if we're restricted to either of those. So degrees. See that little circle there? That means degrees. So we need to be able to turn, and we can either think about it like this: 1 1/4 of a wave. Okay, because remember, it's a quarter of a wave, but there's a full wave between it. In other words, 0 degrees phase difference between Q prime or 360 degrees, right? It's kind of because there's 360 degrees of phase in a wave, then you could report that phase difference as 360 or 0. It's like, well, that's where the wave repeats, right? So we could, there's like 2 sort of correct answers. One would be, well, it's just a quarter out of phase with like that starting position. And a quarter of the entire phase of the wave is 90 degrees. All right, so it's out of phase by 90 degrees, a quarter of a wave. But if we say, well, there's 360 degrees of phase between Q and Q prime and another 90 degrees, then what's 360 plus 90? And squares, no borders. I guess you would never do a 360 plus 90. You would never do a 450. All right. So I guess that's the correct answer too. We'll check the mark scheme and see if they would have allowed 450. I feel really good about 90 degrees because you can just kind of consider that Q prime, what we call Q prime up to point R there, and that's 90 degrees. But if you do consider, well, Q is a wave over, you're sort of accounting for that with this answer, right? Like it's a whole wave over, and then another 90 degrees from like where that Q prime starts. So I think that's a good one to check the marks. They would allow 450 degrees as a answer. In skateboarding, I guess you would never want to land 90 degrees off. Like if you do a 360, right, you spin all the way around, right? Your wheels are sort of back in line to like land on the ramp. But if you do a 450, right, then that's a wipeout. Okay, if you leave like a half pipe and you spin around 450 degrees, your wheels are perpendicular to the plane of the ramp when you land, and it will either be a cool like new trick you've just invented, but it may spell disaster. I think the frictional coefficient would not be in your favor there. So years ago, Tony Hawk, for the first time in 900. Okay, I think people are doing 1080s now. Okay, they're doing like 1080s now. So that's 900 plus another 180. So it's always got to be multiple of 180, right? You can't get a multiple of 90 in there. Oh, we got to track it. Good to relate it back to familiar things for us here in Florida, like snowboarding, right? Like, oh yeah, all that snowboarding we do. All right, figure 4.1 shows the position of the string at time t equals 0. Describe how the displacement of point Q on the string varies with time from 0 to 0.01 seconds. Okay, so at time 0, we're looking, remember they told us this was 1 instant of time, and they're still asking us to refer to this figure. Note that they gave us a time to consider here that is what? Half of this. Right, they said, hey, what's this going to look like? They said, where's point Q going to be? Right, 0.01 seconds later. So how we're interpreting that correctly? Figure 4.1 shows the position at time 0. Describe how the displacement of point Q varies from 0 to 0.01. All right, so point Q over here. The energy is going like this. Okay, think about it. Before the energy got here, you just had a horizontal string. All right, but then some energy runs into it and it goes, makes the string start going like this. And so the points here are moving like this, up and down. Right, this point Q doesn't go on with the wave. It's part of this string, and it can't sort of, all it can do is go perpendicular to the direction of energy transfer. See how this wave cuts across the direction of the travel of the wave, right? So across, trans, okay, trans means across. So it's a transverse wave. The wave particles are cutting across the direction of energy transfer. So let's see, if point P is down here at a trough, it's going to be moving up, right? And so like as that moves up, this point's going to move down to a trough, right? It's kind of like the trough is moving, you can think about it like this. Like this trough is moving over like this, right? And so like as point P is going to move up, it's going to kind of pull the rest of the string sort of like, that way, right? So 0.02 seconds later, everything is back to where it started, right? So like this point is back here. So half of the time period, point P is going to be up here, right? And the wave is going to kind of look like this, right? So at that time, it's going to kind of go like that. Half of the time period of the wave later, right? Everything kind of goes from here to here. So point Q actually doesn't change, right? It's still where it is. But this point would be down here, this point would be up here, this point would be here, but all these wouldn't be displaced. Or would it? Let me make sure I think I do this. The wave, okay, half a wavelength, so it's going to be here. So, yeah. So that's another way to sort of think about it. It's like the trough is moving this way. And so, time period later, like this trough that is the energy that's made the particle move here. Right, like energy travels to here. The particles just are the medium that energy is going through. So that full wavelength to get through. So the trough has made it to here, right? And that's why that's the correct waveform. And so yeah, 0, right? I feel like the answer is 0 for this. See how I'm just kind of thinking my way through it, just kind of talking your way through it, going, okay, this makes sense, you know, and it's like, oh, wait, am I sure about this? Paper 2, you might have enough time to do that, right? Like you got 7 or 8 questions, and they're all kind of like pretty straightforward if you've been studying the physics. You know, it's nothing as tricky as paper 1. Some paper 1 questions are pretty tricky. Paper 2 is usually pretty straightforward. You know, like if you know the physics, it's you know, it's nothing too tricky about it. So I would say the displacement of point Q, you know, doesn't change, 0. You kind of put that in your own words, right? Like point Q just kind of stays there as the wave sort of travels through it. So we know that by the time 0.01 seconds has elapsed, it's still 0, but does it change along the way? That's what I'm trying to think about right now. Like, does it move up and then back down at all? Kind of like the energy goes like this, and everything is kind of, yeah, I don't think it changes at all, right? It doesn't. This is where you want to like simulate it. What's going on there? Something you don't really get the benefit of doing in the middle of a paper 2. Let me pull up a simulator here and have a look at this. And really, I just kind of want to point out these resources to you because it really is helpful to be able to like see it, you know? So this is one of the PhET simulations called Wave on a String. And it's kind of like, all right, let's give ourselves like an oscillation here. Let's have it have no damping, like the wave stays. And I don't want to fix that unless it have no end. So that wave goes out the window there. All right. And now pause it. There. So we kind of had, right, like this. So it was, this point Q that's at equilibrium as the wave kind of moves through, right? So it's like this point here that's at equilibrium. Like as this wave goes through, kind of focus on this particle right here. Oh, slow motion. This particle right here. I wish we could get a green one. So it's on equilibrium, and then as this trough moves to here, what's going on with this particle right here? All right, let's kind of focus our attention on that. All right, ready? Here we go. So here's the particle at equilibrium, and as the trough sort of goes from here to here, what happened to that particle? It goes down and then back up, right? That makes sense because this trough has to go through it. As the trough is moving this way, it's pulling all these particles down. So Q actually goes down to here and then back up in that time, right? It's not like it doesn't move. It's not a stationary wave. Yeah, okay, I think the next part of the question is like, no, stationary wave is, right? And that's when it's not going to move at all, when the other wave comes back and interferes. And so let's not conflate those two ideas like Kyle did in my mind. It's like, wait a minute. And that's why I have to be really careful, right? Go back and say, this is still a progressive wave, but you have to reflect it. And so as this trough gets to this point, it brings this point down. Like this is the point on the string that occupies this position, but the trough sort of has to get there, right? The energy that's making the particles displace like this goes. And so point Q goes down to this, after not 0.01 seconds, but after 0.005 seconds, point Q is down here at the trough, right? It gets a chance to get the trough. But then as the trough sort of continues moving, right? So this point went down here. Now it's down here, and point Q is back up here. So 0.005 seconds, point Q goes here, then it's at the trough, but then another 0.005 seconds, and it's back up there. Did anybody sort of realize that before I queued up the simulation? Because some people are really good at that, just visualizing this in their mind, and I think some days I am too. It's just not one of those mornings for me. I don't have a good enough breakfast. I'm like, wait a minute. It's like something in the back of my mind didn't feel right about this thing. Well, it's zero, but it doesn't stay at zero, right? It has to go down to the trough and back up. So that, and I guess, I've been doing these papers for years and years, you guys. And so anytime there's this many lines for an answer, 2 marks, it couldn't be that straightforward, right? Like, why give me all this space to write my answer if it's just as simple as like, it doesn't move. So it does, right? In 0.005 seconds, it moves down a displacement of, whatever the amplitude is. It goes down to the trough, and then it moves back up. So describe how the displacement varies. It's not saying, hey, what's the net change in position? Because then the answer is 0, right? Over that time, it is 0. But how does it change from 0 to 0.01 seconds is that it goes down to the trough position after 0.005 seconds. And then after 0.01 seconds, it is back up to equilibrium position. So that the total change in position is 0 over that time, but it still does displace over that time. That's how it varies over that time. And it'd be up to you to kind of put that in your own words, and 2 marks for that one. So do that kind of a question justice there. If you have any questions about that, leave it in the comments below. Or ask now if you're in person. Do that. The people, that are watching this video centuries in the future, are like, oh, okay, let me check the comments. Okay, but some of you are here right now as it's happening. So think about that. Oh, wow, yeah, I was here when that happened. A stationary wave is formed on a different string that is stretched between 2 fixed points. I think as I my eyesight went down to that part of the question, I was getting in the mode of like, okay, stationary waves and no displacement, thinking of nodes, right? And so I take, treat it one step at a time. So we have a different string now. We got 2 fixed points, X and Y. Figure 4.2 shows the position of the string when each point is at its maximum displacement. Okay? Explain what is meant by a node of a stationary wave. Very much like a definition, okay? If you look in your notes, you probably have a good textbook definition. So it's a point on a stationary wave with 0 amplitude, okay, with no displacement. A point on a stationary wave zero, and that should agree with your notes. State the number of antinodes of the wave shown here. All right, so here we find a node, here we find a node, here we find a node. And so where are the antinodes? Remember, they typically will be friendly enough to show you the loops. In other words, they always show the wave as it exists now, and it's nice if they show you the wave as it exists half a time period later, right? Like when this point's here and when this point's here. Because that's the interference. It's like this wave and this wave. The energy from both of these, waves interfering with each other, making the particles sort of displace either none or more than they sort of should, right? Antinodes or nodes. Take the number of antinodes of the wave. So how many? Question 2, right? Part 2 of C. Oh, I thought he gave us the answer there. There's an antinode and there's an antinode, right, where the particles are moving along. State the phase difference between points W and Z. And they want it in degrees here. Students that say, all right, well, here, this is at the crest, and oh, it's not quite at the trough. The trough is down here. It's like halfway between there, and they start to think about how much of like this is 108 or this is 90 degrees. This was half of 90, 45, and they're doing that. They're forgetting a key idea, right? What's the key idea that a student that tries to like, oh, what's half of 90 is 45, and I got to add that to. You just have to say these points are occupying what? Adjacent loops. Like there's a loop, and all of the particles. All of these particles and all of these particles are what? 180 degrees out of phase. That's 180 degrees out of phase. You're either in phase or you're out of phase with a stationary wave. You're either with us or you're against us. Okay? You're not 45 degrees in between. But only the SIP feels in absolutes. I am wearing my Darth Vader mask, you guys. Poor you. That'll work out. A new stationary wave is now formed. Wow, this one never ends. Okay, the last one. 11 marks on this. This is a bonus 11 point here. A new stationary wave is now formed on the string. The new wave has a frequency that is half the frequency of the wave shown. The speed of the wave is unchanged. On figure 4.3, draw a position of the string for this new wave when each point is at its maximum displacement. Okay. So we want one with less frequency. Again, this is where like seeing this in the lab is helpful. Remember when we took a slinky out and we created some stationary waves and I said, I want a high frequency wave now. What did that do? I had to move it a lot faster. Like I'm in control of the frequency. Like how many waves per second? That's what frequency is. So I'm shaking my arm back and forth how many times per second, right? Making a high frequency. And when we did that, what did we see? A whole bunch of nodes and antinodes, right? That's when we had a lot of nodes and antinodes. So if I decrease the frequency, I'm gonna have less. Well, what could be less than this? I got one wave here. What's less than one wave? Could I have a quarter of a wave? Is this an allowable frequency? Remember that idea. Certain allowable frequencies. Could I have that, a quarter of a wave? The fact that this is pinned down right here prevents me from having an antinode at that point, right? I can't have a quarter of a wave, but I could have a half a wave. See how this is physics, you guys? You got a thing like this and a little eyeball and a wave inside. So you could have this frequency, right? This would be allowable. That's the fundamental frequency, right? When you're thinking about something that's pinned down on both ends, like a guitar string that you pluck in the center and it just goes with that sound effect. So that's what we should draw. All right. Let's go down here and put it on the right part. All right, hey, that worked out well. Now I think we should only draw one of those though, because it says draw a position of the string for this new wave when each point is at. And so you could either draw this or you could draw this, but you wouldn't draw them both. So remember that the string can actually only exist here or here at one instant of time. It's not in both places, even though it may look that way. Like if you pluck a guitar string, it goes so fast that our eyes basically can't keep track of that changing position. So it does look like a blur. Okay, and it does look like it's occupying both positions at the same time. But we know, like, if we were to take a picture, a snapshot at one instant of time as this question began, we'd either see it here when the points are at maximum position, or we'd see it here if it's at maximum displacement. If it's at equilibrium, we see all the string like this. So like the guitar string is like this, and we pluck it, and it goes from here to here, vibrating back and forth at that fundamental frequency. Okay. And again, based on the length of this string, only certain frequencies would be allowed, which is why the skill of a guitar player is like, okay, if I put my finger here on this fret, I've shortened the length of the string by that amount, and now this frequency will be allowable. And it's a different note, right? The frequency is a different note. This has been paper 22 from May, June 2020, AICE Physics 9702. We'll see you next time.